This is a really great session, and this yesterday was our first go, so this will be the second day. And I was really excited coming to this just because of the other presenters who I've known and had so much respect for, and they have so much knowledge. So just being part of this and seeing it come together yesterday, definitely excited for today as well. So I was asked to do the opening overview, was given a little bit of a few prompts related to taking the conceptual site model and starting to look at remediation strategy. So I'd like to say that remediation is easy as 1, 2, 3. We know it's not always easy, but these are 3 very important steps. These are my 3. Brandon will show his. I think he's got 5 important steps, but this overlap. And what we're going to see throughout the day and through all the presenters is some of these common themes of starting with developing your conceptual site model, characterizing the area that needs treatment, not just at the nature and extent component, but how well do we understand where the remediation needs to be eventually done? Where is the contamination? How is it distributed? From using that, the next step is a remedial design that is built around the contaminant site model. Where is the contaminant, and how do we deliver our remediation, whether it's even if it's as simple as excavation or an injection or thermal. And then the last and really critical piece is the remedial action. We can have a great remedial design on paper, but we need to be able to implement it in the field using the right tools to be able to get the contact, to be able to get the delivery, as well as in the 3 dimensions where the contamination and how the hydrogeology sets up. So what sites are good candidates for in situ remediation? Many sites are. Because we also have many different tools which will be presented today from the different presenters. But one of the most important questions to ask, and each of the presenters as they go through their technology, we'll kind of touch on this through different more technology specific, is the contaminant amenable to treatment? If that's the case, then we can at least start proceeding with considering that and doing a little more detailed evaluation. We also have to ask about what is the geology, what is the hydrogeology like? Can we move fluid through a pore space? And that fluid can be liquid, can be slurry, can be gas, but we want to be thinking about the hydrogeology, the permeability, the effective porosity. And then even if there are low hydraulic conductivity sites, we have remediation alternatives for those as well. Thermal remediation, fracturing, soil mixing, or even just excavation. These are some of our more common contaminants that we come across in a hazardous waste field, with petroleum hydrocarbons, chlorinated VOCs, metals, 1,4-dioxane. And really the take-home message with this is that with these different key contaminants, we have options. And how that decision gets made at any one site there's various factors, and we'll learn more about those from the presenters as we go forward. But there are many different technologies, and these can also be combined as well. So the feasibility study is an important step of that. I've spent a lot of time implementing and thinking about feasibility studies over the years. But when I was my dozen years as a consultant, I was involved in many feasibility studies. Now at ISOTEC, I'm often contacted and like, oh, here's the site and these are the contaminants. What are we thinking? A lot of times the consultant or the regulatory agencies or the client are at a point where they're evaluating different technologies and they're looking for some input on terms of whether it's cost, implementability, potential downsides of different technologies to help that remediation process. And then just one other note, in the class that I teach that I'm going to tonight, their final project is to complete a feasibility study on an actual brownfield site. So I think it's a really great exercise and a really important exercise, and where there are certain criteria, but we're really thinking about getting us to making a decision about what's the appropriate technology or alternative that may include a combined technology approach for a given site. And based on what are the contaminants, what is the impacted area, how big is that area, but also where in the plume is that? Are we in the hot spot? Are we downgrading? Are we mid plume? That's going to affect some of that decision making. The depth, current or future site use. Is the site looking to be redeveloped into apartments in the very near future? Is this a manufacturing site, or is this an open field that's going to remain that way? And then that'll also help to determine what our objectives are and what criteria we may be looking to go after. And the technology screening step is a really important part of that, as at the front end of the feasibility study of starting with the universe of possibilities. What are all of the potential technologies that might be applicable at this site? Then we start asking our questions as we go into screening about, well, is that technology effective for that contaminant? Can it be implemented on this site based on the depth, the soil type, the site use, future site use? And what are a magnitude of costs? Are those costs for that technology within the budget that either that client has or the like? And it really, that screening helps to determine which technology should get more detailed evaluation and which one shouldn't. And it's always better to go through this technology screening process than have your client, your regulator, the program manager ask, as you get further down the line, well, did you consider X? And you want to say, yes, we did. And we screened it out because of this, this, and this, as opposed to going, so as we start getting into our screening, our feasibility studies, and then eventually selecting a technology, the really important question to ask ourselves for any site is, do we have enough information to make a remediation decision? And do we have, where does the remediation need to target? That geometry of contamination is a really critical part of it. And then from that understanding, is our conceptual site model fully developed? Do we need further bench scale testing? Do we need some pilot testing to help fill in some of these knowledge gaps so that the remediation, we can make appropriate decisions and design and implement with success? And a key component of this is recognizing that the resolution for characterization is less so than what you need for, let me say that. The level of characterization that we need to remediate for remediation design and decision-making is much higher than it is for delineation. Delineation checks if the contaminant is present and maybe how far it went, where remediation really needs to understand how to target the contamination. So I've got a sweet tooth, sweet tooth in the room. All right, so here's a good analogy. So the remediation characterization, if we think about the remedial investigation phase, delineation tells us how big the cake is. How big is that cake pan? What's the diameter? Is it a circle? Is it a square? How high is it? But we don't know anything about where it is within that cake pan. We don't know if there's layers. We don't know. So the remediation characterization tells us what's inside the cake and what tools we know to we can figure out how to eat it. Right? If it's an ice cream cake versus a layered cake, do you want a spoon? Do you want a fork? Do you need a knife? We got to figure out what tools we need based on what's inside and what that cake looks like from the inside. So if we take that layered analogy and then go into some actual data, one of the things that our industry relies on very heavily are monitoring wells. They are relatively easy to put in. Many sites already have them. They are where they are. They're the lengths that they have. And they tell us some level of information. But it's often over, there's 10-foot screens commonly because that's the length they come in. You take it out of a bag, you put it in, drill to your depth, you put a 10-foot screen in. We've all done it. But that doesn't tell you anything about the geology, the hydrogeology, where the contamination even is within that 10-foot zone. It just tells you a screen over 10 feet. So we look at some of the soil data. Oh, excellent, works today. Didn't work on the screen yesterday. But this is a diesel fuel release site, and groundwater high tables here, groundwater low is this white line. But what we see on several of these locations is that over even 1 foot or even 2 feet, these are soil concentrations. DRO concentrations change by orders of magnitude, 1 if not 2 orders of magnitude at times. So you've got 62,000 at 26 feet. At 28 feet, it's 100. That's a significant drop off. And if our monitoring wells are 5 feet or even 10 feet, and if the geology is different across that 10-foot layer, what's coming into that well may be highly impacted by the much less impacted zone. and we don't have a sense that how high this is. And we even see on some of these that there may even be, like if you had a 10-foot screen here, we may think we have to treat that, but all of the contamination in a lot of these locations is only maybe 2 or 3 feet thick. And these are the things we want to know so we can ultimately develop a surgical remediation plan, right? Having a bit of a laser focus in our planning so we know exactly where the contamination is and where it isn't, as well as where is it really high and where is it moderate concentrations. We can direct and make decisions based on that as well. Another reminder is that where is our contaminant in the subsurface? As I said, we have a heavy reliance in our industry on monitoring wells. But for most of our common contaminants, most of our organic contaminants in particular, the VOCs, petroleum hydrocarbons, even PFAS to some extent, most of the contaminant is not in the aqueous phase. And even when there's no NAFL present, the significant portion is sorbed to the soil. And that's affect to the fraction of organic carbon in the soil, the organic partitioning coefficients of the contaminants. But roughly rules of thumb, I would recommend that consider that 70 to 90% of your contaminant residual mass is not in the aqueous phase and it's partitioned to soil, or maybe a little bits of NAFL as well, or maybe a lot of NAFL, depending on the site. And this partition mass can be a long-term source, a source of rebounds, and why we question, well, we did an injection and the concentrations went down really, really quickly, and then they came back. And to not say that technology was a failure, but to recognize what we treated and what we didn't treat. And then there's a whole heterogeneity of soil in that no site is homogeneous. And even on Cape Cod, where we think like, oh, it's all sand on Cape Cod. I've got a boring log that I'll show later in my PRV presentation. But we can see here, and it's a little bit bright here, but this is a 10-foot by 10-foot by 10-foot test pit. And there's clay, there's sand, there's boulders that are this big, there's cobbles, there's gravel, and this is all within 10 feet. And if we were to run a boring here, we can see the clay layers here, and it's a little light here. So if you can take my word on it, you can see the slides, and we have sand below. But if we moved over, this is 3 feet. Now the clay is at different depths. The clay is different thicknesses. There's more clay down here at this level that's not at this level. So there's just variability. If we move over this much, this much, this much, this much, and if we're lucky on a lot of our sites, our borings are 20, 25 feet apart. If we've got really tight borings, more often than not, they're probably 50, 100 feet apart. And we're seeing this level of geologic variability in a 10 by 10 by 10. I love cross sections, I do, but that's the discrete level of data that we have, and we're trying to connect dots that are 50 to 100 feet apart. Another one of my recommended phrases is follow the contaminant, not the sample. I've already talked about monitoring wells. This was a case study where ISOTEC was contacted by a consultant and said, we've got 10-foot monitoring wells, 20 to 30 feet below ground surface. Can you provide us, this was a petroleum release site, can you provide an in situ chemical oxidation quote for treating 20 to 30 feet? I said, okay, we can definitely do that. But is there any other information? Do you have boring logs? Have you done any high resolution calculations? I said, yeah, we did a laser induced fluorescence. And one of the things, also to point out, this was a primarily silty sand with some clay for geology, but they sent over the laser induced fluorescence. So I'm just going to walk over here for a minute. And the results here, this blue arrow is the 10-foot zone that they asked us to provide a quote for. But this, you can see in this zone of maybe only 3 or 4 feet, is where all the contamination is. So I'm not saying there's no contamination at the top or the bottom, but the significant portion of the contamination is actually coming in this very small zone. So we can create a design and implementation plan that really focuses on this level of mass, because this is where most of the mass is, and not having a uniform delivery across 10 feet. From a conceptual site model hydrogeology perspective, there's a pebbly sand and pebble zone right around 25 feet, right where this is. So this is a predominant silt and clay site with a zone that's higher permeability where all the contamination is. So this is bringing together what do we know about the contaminant profile, as well as hydrogeology conceptual site model to be able to design and implement based on that. That goes back to that 1, 2, 3 starting with. So as another case study of this is a site in New England, former mill building, right? We have mills all over New England that was being redeveloped into low-income housing. So really valuable projects. Impacts from the historic manufacturing of PCE and TCE, site soils, I'll show in a cross-section in a minute, some fill, some organic silt and sand, and then an outwash below that. And there was a preliminary treatment plan that came to us from data collected prior. It was about 4,000 square feet, so not that big. But the focus based on the data that was on this upper fill and organic soil level. And it was about 4,000 square feet. So here was the data that we had when we started, PC and TC, soil in milligrams per kilogram. So 4 and 5 and 22 milligrams per kilogram, pretty stout numbers. And then 2 monitoring wells. We can see this one is a 10-foot. We have a 15-foot monitoring well. This one has the highest concentrations of CVOCs. And the blue dotted plan here is really where the remediation zone was going to focus on. So we looked at it and said, well, do we really, and just to point out, there's 1 soil sample at each boring. There were some PID readings that was helpful, but we had one soil sample. So we're kind of limited in what we might know. So it was recommended to do a little bit of additional remedial design characterization. Relatively small area, so we recommended 6 additional soil borings and collecting soil every 2.5 feet. So we get a much better vertical profile of that. And lo and behold, we find these whopping 120 and 500 milligram per kilogram concentrations of PCE at depth. This was below the zone that we had proposed or that had been recommended for treat. So given 6 additional borings and finding more contamination deep, one of the things we did find is that this lobe out here, we had 2 more borings. This was not impacted. So we were able to take this out of the zone. And then we had this area to the south here that wasn't even in the initial plan that was impacted as well. So we ended up changing the treatment area, and it went from 4,000 square feet to 2,700 square feet. So actually a smaller footprint. We went with a deeper treatment interval, and we're able to put more reagent at that deep zone where the highest concentrations were. In the end, the volume of soil to treat was the same, and the cost was plus or minus the same. So from what was originally budgeted, we were able to take that same level of effort, but really apply the remediation where it was needed, just having a higher level of remedial design characterization. So just at the overview step here, it was also wanted to look at a few different other technologies that may be a fit for a site. We're going to spend a lot of time with in situ technologies going forward. So this is probably about one of the most aggressive you can go with. It's just excavation. And it's physically removing of your soil. It can also be sediment. You're also going to, if you're below the water table, remove some level of impacted groundwater as well. It's a readily available technology, readily available equipment, and for speed, this is one of the fastest remediation technologies, and there is benefit of that. If the objective is to get the contamination off your site or off this particular site and just get it out, technology, this can be a very effective technology. Where dig and haul might be the best option? It's the schedule. Speed is one of those pieces. Is the contamination accessible? If it's shallow soil, that's often a better fit. Shallow soils sometimes are not a great fit for injection of fluids or even for heating. Unsaturated soil is a little bit easier than saturated soil for excavation. There's no dewatering component to it. And some of the best fits for excavation or well delineated contamination. The last thing you want to have is an excavation plan where you have your excavator and you have an open hole. You do your sidewall sample or your bottom sample and you realize there's still a whole lot more contamination here. So now you have an open hole that has to stay open much longer than that's desired. And then one other place where excavation works really well is if there already is excavation part of redevelopment. There's a number of projects that I've seen over the last few years where they want to build subsurface parking. They're already going to be excavating large portions of the site to 20, 25, 30 feet. And if there's some contamination over there, it's while you already have your equipment out and you're planning to just excavate that and take that as well. The places where a dig and haul might not be a good option, where there's a lot of subsurface utilities, depth, excavators are typically limited to 18 to 20 feet. So to go deeper than that, it does require some kind of benching, significant shoring, other earthwork that just makes it more complicated, more complex, and therefore more expensive. Same if there's buildings, contamination below the water table will require a whole dewatering plan and implementation. Water treatment, if we're talking about a hazardous waste site, that groundwater is contaminated, that's why it's being excavated. Depending on what your contaminant is, the concentrations, what are your disposal options, offsite disposal can get costly. And just as a recognition for all of us, both as practitioners and as the regulatory community amongst yourself, there is a preference, as well as us, I think, as environmentally concerned citizens, a preference for destruction. Let's not be taking our contamination in from here and just dropping it over there. Some of these challenges, there are mitigations in terms of benching, shoring, dewatering, dust control. So if some of these conditions where excavation may be more challenging, we as industry have mitigations for that. And modern natural attenuation is a less intense. It's not a no action, it's not a do nothing alternative, but it is a less intense remediation alternative. And what it is, it's relying on natural processes to decrease or attenuate the contaminant in soil and groundwater in the mass without direct human intervention. So we as humans, as remediation practitioners, are not involved in the actual actively treating the contaminant, because it's happening by biodegradation, dispersion, dilution, volatilization, other chemical reactions in the subsurface. So modern natural attenuation as a remedial alternative, we're still collecting soil and groundwater samples to assess the concentrations, to look at site characteristics, to look at trends. So as I said, it's not a do nothing alternative. And natural attenuation is occurring at most sites to some extent. Do the right conditions exist, as well as how fast is it happening? Yes, with this contamination, and it may continue to attenuate over 1,000 years, but is that acceptable? Or maybe it's on more in the order of 5 to 15 years, and so sometimes it's better to not just let the existing natural reactions run their course, because they are reducing the contaminant mass and therefore the risk as well. And if we can see existing trends, that's a better fit for modern natural attenuation sites. If there is ongoing biodegradation, we can document that through microbial analysis, through byproducts, through the appropriate conditions. It is a way to have our concentrations continue to decrease. So if we're thinking about modern natural attenuation, and we're at least want to evaluate it before we select that remedy or after even selecting that remedy.
Wait, it's in the process. Let's see.
All right, don't touch the bottom button. That's bad.
Noted. All right. Thanks, Amazon. Oh, jeez.
So what are we looking at?
Go with it.
Our contaminants. Some of the reaction products, if it's reductive dechlorination, lesser chlorinated products, ethene, ethane. If it's a petroleum site, looking at concentrations of carbon dioxide and methane, other natural source zone depletion parameters, particularly maybe the target bacteria. If we can quantify that the bacteria that we desire at our site are there and healthy concentrations, that's a great sign for modern natural attenuation. I'm going to be the first and not the last today to talk about the importance of water quality parameters, dissolved oxygen, pH, ORP, conductivity, temperature, really critical for evaluating really any in situ remediation technology, but especially for modern natural attenuation to understand what those water quality conditions are, and are they favorable? Are they continuing to be favorable? Are they changing? Are they becoming more favorable from M&A or less favorable? just some recommended resources that, for remedy selection, the Enviro Wiki, it's a bit like Wikipedia, but it's filled of remediation, good stuff. Certain ESTCP websites and where those innovations are happening, cluing. And then I have, some just guides for excavation and natural attenuation from EPA. And this USGS framework for assessing sustainability of M&A is a really, really great reference, that I spend time with periodically. So with that, I thank you. I look forward to the rest of today. Do we have time for a few questions?
Oh, yeah, we got 13 minutes.
Okay, good.
Any questions or online?
No, it's early. All of your questions the rest of the day, because then we'd all just go home or overnight.
There's one right here. So when you talk about your feasibility study and the advantages and disadvantages of different technologies, at the state of Vermont, we use like a rubric to kind of score those options. Do you do something similar or recommend something similar when you're looking at the different options?
Sure. So, I mean, I'm sure most states' rubrics are somewhat trickle downs from the NCP criteria, right, the 9 criteria. Some states have modified those slightly, maybe have added something like that. So, I mean, if you're working in a given state or on a federal project, you have to go through those rubrics. And those rubrics have value, and because it is effectiveness, short-term risk, exposure to site workers, things like that. The ability to meet criteria. So those are good. And typically a lot of times cost and budget become the ones that kind of come to the highest weighting. But yeah, so that's a great place to start. I was involved in a presentation. I didn't give it, but there was a group of us who assembled this at the AHS conference last year. And I can send the slides if anyone's interested about how those criteria are good, but in kind of reevaluating sites in perspective of risk assessment, site reuse, sustainability, and environmental justice for that matter. Some other criteria, and we were looking at it, calling it a community site model. And because when we make decisions on remediation of this site here, we're also, we can't, like, we often think about, well, who are the adjacent property owners? Who's right next door? Who's across the street? But that decision here affects a much broader community. And if it's an excavation site, it's, well, where is that soil going? Whose community is it being driven through? Who is it being disposed at? If we're thinking about, and this is not a matter of doing nothing, but this is, you know, where M&A actually may have some value at times, or in situ remediation versus where there is if you're thinking about operating an SV or biospark system, or doing an injection, or letting natural source on depletion continue to run its course, depending on what the risk is at a site and where it is, because then that's maybe using electricity for 3 years. And when we're thinking about remediating this site, but as environmentally concerned citizens, we should also be thinking about global warming and the bigger around us. So depending on who's providing that electricity, is it a coal power plant? Is it nuclear? Is it wind powered? And considering running a system, not to mention, you know, the other factors that go involved in that, is that something that should be taken into account? And that's not taken into account in the 9 NCP criteria.